Hello everyone, my name is Seerkamban Elangovadikal, matrix number AE210073. And today I would like to present my smart health monitoring system for chronically ill patients. So I'm in the fourth year for the year 2024 to 2025, and my supervisor is Encik Nick Muhammad Asri bin Nick Ismail. These are the chapters we'll be discussing: introduction, literature review, methodology, results, discussion, and conclusion. Okay, for chapter one is the basic introduction. Prioritizing health is crucial for overall well being. To improve healthcare and quality effectiveness, it is essential for continuously monitor patients' parameters such as autonomous nervous system activity using non invasive sensors. The health monitoring system, aka HMS, has become a complex technology with advantages over traditional systems. Sensors can also be used to monitor chronic illnesses and rehabilitation advancements, offering effective data connection for remote medical treatment. So, problem statement and objective. So, for problem statement, the traditional healthcare system faces challenges due to chronic diseases and the need of continuous health monitoring. Current methods often rely on periodic assessment and reactive interventions, leading to delays in diagnosis and suboptimal treatment outcome. The project investigates the feasibility of the continuous monitoring key physiological parameters using non-invasive sensors, the lack of affordability, user-friendly systems offering continuous monitoring, real-time analysis, and remote accessibilities is a significant gap. The project aims to develop a HMS that tracks vital signs like heart rate and body temperature, transmits data to a cloud for real-time analysis, integrates diagnostics feature, provides preliminary health assessments, and triggers alerts to detect anomalies. So, for objective is to develop a effective smart health monitoring system and to evaluate the performance, accuracy, and reliability of the system using comprehensive and rigorous testing. So these are the project scopes: is to develop a hardware and software for healthcare data collection and system integration features, as well as testing, evaluating the device and system, as well as project management. So for chapter 2, literature review, this is for the SpO2. SpO2 is the percentage of saturated oxygen in hemoglobin relative to the total hemoglobin in the blood. It tells you how much oxygen is the blood carrying. So normal range is between 95 to 100. SpO2 is may trigger alerts in the system. 84 to 94% is considered hypoxemia, low blood oxygen, and 85% may indicate cyanosis, which is serious lack of oxygen in the tissue. Measured using oximeter sensor like MAX 30102 and Osram SFH 70702 using red and infrared light absorption LEDs. Now for the heart rate. So heart rate is actually the number of times your heart beats per minute. That's why we call it BPM, beats per minute. It reflects cardiovascular and autonomic nervous system health. So the normal range is between 60 to 100 BPMs for adults. Abnormalities, if it's below 60, it's called barcardia, which is abnormal slow heart. If it's over 100, it's tachycardia, which is abnormality fast heart rate. So it's measured using a pulse sensor and oximeter, just like before, using a PPG. So for temperature, the core body temperature reflects the body metabolic and immune system status. The normal range is between 36.1 and 37.2. So there are extreme conditions. That if it's below 36.1, it's hypothermia. If it's above 37.2, it's a fever. So usually it's measured using an infrared sensor like MAX 90612, or what I'm using, a thermocouple K-type sensor. So this is our block diagram. The block diagram starts with a user vital signs like body temperature, HNO2. The data is sent from microcontroller for processing and control. The module interprets the forward data using to a user interface accessibility via mobile app or website. User interface is crucial for visualization of health data and enhancing active participation in data analysis. The system extends the alert and notification over detection of anomalies. If further medical evaluation needed, the system diagnosis can be done in a medical facility for further analysis. The system flowchart outlines the process, measure temperature, HR, and SpO2 for user collection, data formality and control, microcontroller process the data, user interface, Arduino IDE, diagnosis generation, analyze data develops using preliminary diagnosis, diagnosis to a medical facility, further evaluation is conducted at the facility. So this is a flow chart. So the user measure vital signs like HR, SpO2, and specific sensors. Heart rate is measured with a normal range of 60 to 100. Bradycardia, which is below 60 ppm. Tachycardia is over 100 plus. O2 level is measured within the range of 95 to 100%. 85 below 85 is cyanosis. Hypoxemia, which is 85 to 94%, and normal if it's 94% and more. Body temperature is checked within 36.1 and 37.2 degrees. Hypothermia is below 36.1 and fever is 37.2. The system generates a diagnosis report highlighting the status of commending necessary actions. So for the system overview, the green LED emits a light to the skin, usually at the fingertips. Photodiode detects changes in reflective light caused by blood volume pulses. These pulses appear as peaks in the analog signal. The system detects time between peaks to calculate the beats per minute. So the formula is 60 to T peak, 60 referring to 60 seconds per minute. So for temperature, the tape-type thermocouple produces a small voltage in millivolts based on the temperature. This voltage is amplified using an op-amp like LM324. Arduino reads the amplified voltage and converts it into temperature. So the temperature formula is V minus 50 over 16 plus 24. The V is the voltage read at the sensor, 50 is the voltage at room temperature, 16 is the constant for temperature over voltage, and then 24 is the degrees in the room temperature, so 24 degrees Celsius. So now for the SpO2, the device alternates between turning red light and LED, red LED and infrared LED for each reading of the analog signal of the photodiode. To calculate SpO2, the sensor must capture how much light is absorbed between two wavelengths. Red, which is 660 nanometers, and infrared, which is 880 and 940 nanometers. Red LED is when the red LED is on. IR read is when the IR LED is on. DC component, which is the constant, which is the average signal baseline from the tissue, bones, etc. AC component is the peak-to-peak fluctuation caused by pulsing arterial blood. The system then calculates the ratio between the absorption to estimate oxygen saturation. So the ratio we'll calculate is AC red over DC red, divide by IRAC over DCIR, and then we'll use this formula SpO2 equals to 110 minus 25 times R. So this is a picture of the earliest prototype I developed. So the BPM works with oscilloscope raw noisy, which works with noisy SpO2 and use transistors to pre-amplify the raw signal using a cap to filter noise R2. So it uses the LM324, uses one transistor to make a square wave. So this is the schematic diagram. And the next page will show the code for the Arduino IDE and the top view of the health monitoring system. Okay, so this is my device that I have over here. Sorry, it's a bit tangled up. So this is my this is the probe that is going to be used to measure temperature. This is going to measure the SpO2 oxygen blood level saturation. And this is the one that will be used to measure heart rate. So for the heart rate, I put two AA batteries in here, so it can power the green LED lights for it to bounce to measure the heart rate. Okay, this now is showing the diagnosis report. First, let me put the temperature uh, sensor on my neck. Okay, roughly we have at least 29 to 30 degrees Celsius. Now I'm going to use this sensor, the Osram 7072 heart rate sensor to measure my heart rate. Initially, I want to use this to measure my heart rate as well as the blood oxygen level, but due to the complexity, I have to use the max citron sensor to measure it. So this switch is actually supposed to transition from a heart rate sensor to a SpO2 sensor. So now I'm going to put my finger. Okay, based on the result, we're getting between 90 to 100 BPMs per minute. I mean beats per minute. There are some noises are happening due to the accuracy of the sensor. So I'm going to let it go. I'm going to test now the SpO2. This is the max 30102 sensor. We're going to be using it to measure the SpO2 level. So let's get this on the. It takes time to stabilize, so we should at least get 95. Okay, 96, 98, 98. Okay, so now we have at least 95 to 98% oxygen in our blood. So yeah, this is the results for my device. So for the initial reading and stabilization, the initial reading shows stabilization period. Heart rate is started normal at 77 ppms. Temperature at 33 degrees Celsius and SpO2 normal at 95. Following this normalization indicating a stable state. Stabilized heart rate ranges between 72 to 100. Stabilized temperature is within 36.7 and 37.2 degrees Celsius normal physiological range, and stabilized SpO2 recovered to a healthy consistent rate generally above 94%. Patterns suggest a monitoring device was adjusted before, providing an accurate vital sign data. So for the prototype sensor performance and accuracy, heart rate, which we use the 7072 base module, it's closely matched to the standard pulse oximeter. Agreement within the proximity is within 2 to 3 beats per minute with 92% agreement with a reference monitor. Oxygen saturation using 30102 ranges between 95 to 100% for a healthy Subject typical error sensor, which is between 2 to 3%. Example, a resting volunteer consistently showed SpO2, which is almost equal to 97 degrees within the normal range of 95 to 100, deliver clinically possible XPO2 values. Body temperature, we use K-type thermocouple measures within 1 or 2 degrees with the calibrated medical thermometer. While coarser than the LM335 type sensor, it is adequate to detect fever. Detections above 37 degrees Celsius and elevated fever temperature was expected threshold accuracy. So, in conclusion, the project aims to develop to create an intelligent health monitoring system to help people with chronic diseases. The system uses non-invasive sensors and real-time data transmissions to improve healthcare system. Preliminary testing confirmed that the functionality of the major components include K-type thermocouple, SFH7072 pulse sensor, and MAX 30102 oximeter. Future World will integrate insights from relativity to improve the scalability, usability, and reliability. So the challenges, which include ambient light interference, which is include room lights, particularly fluorescent or LED lights, motion artifacts, which include subtle finger movements, which could affect the accuracy of the measurements, LM324 op amps and high value feedback, which is a trade-off between a gain and noises, limiting the achievable sign to noise ratio, single wavelength SpO2 measurement using green and LED for PPG and IR cut photodiode to prevent any meaningful estimation of SpO2, leading to the erratic and clinical invalid readings, and lack of IoT. It is due to the complexity of the hardware and software and the amount of time used to troubleshoot the required device. Therefore, the IoT wasn't able to be achieved. So for future works, mitigation ambient light interference using a full opaque finger clip and pulse sensor LED system, improve analog system conditioning, replace LM324 with a precise low noise op amp, accurate SpO2 measurement, add a second wavelength LED and use a time division multiplexing. System architecture, improve modularized system for easier troubleshooting and upgrade. Microcontrollers and processing, upgrade to a higher performance microcontroller. Local wireless communication, add Bluetooth low energy BLE for phone and display, and ESP now or ZigBee for low mesh networking. Interference interface and usability enhancements. You develop a PC based GUI for real time vitals visualization. Lastly, is scalability for future integration. Design with scalability in the mind in the future for future versions include additional vitals. That is all from me. Thank you very much.